Morning, ladies and gentlemen. Welcome to our webinar number 3 on performance research on sleep, hunger and driver vigilance. My name is Petra Vladikova and I work for Swegon Air Academy. Let me ask you, how did you sleep today? Did you have a nice breakfast? What are your plans for the lunch? And did you take your car to your job? How do you feel? It's all these conditions that we experience every day have quite large effect on our performance, especially the indoor environment. And today's presenter is David Peter Wyon, who worked all his life researching the connection between indoor climate and performance of adults and also our children. In today's presentation, they will show you what are these other factors influencing our performance 24/7. Such as sleep quality, our eating habits, and alertness when driving the car. The webinar will take approximately an hour and a half, and during the webinar you have the option to send in a question. Just below the video player you will find an image with a question mark. Just click on it, fill in your email, state your question, and David will answer your questions at the end of the webinar. So without any further ado, I would love to give the floor to David, and to all of you, I wish that you enjoy the webinar.
Well, it doesn't seem appropriate to say good morning since we have people online from every time zone there is, and many people will watch this offline. I just want to say that this is the third in a series of 3 webinars I was asked to give by Swegon Air Academy. The first one, which is available offline on the Swegon website, was held in May 2014. That's about a year ago. And it dealt with the performance of schoolwork by children. That was the most topical of the experiments I had recently performed. It summarized the findings of ASHRAE 1257, a multi-experiment project where we showed that warmth reduces the performance of 10-year-old children by 3.5% every degree Celsius over the range 20 to 28. And that poor ventilation also reduces performance. If you halve the outdoor air supply rate, which is easy to do by simply neglecting to open the windows, in some cases, then you will reduce children's performance by 14.5%. And many classrooms, at least in temperate zones, are built with no ventilation, but simply with windows. And they are supposed to be opened, preferably all the time, but if not, at least between lessons. But we showed that the fact is that windows are only opened in classrooms when it's too warm, not to improve the ventilation rate, which is when they should be opened. Now, all that is documented and with the correct references and so on in Webinar 1. Webinar 2 was held in November last year. It's showing 1 here. Yes, sorry. Yes. Well, yes. Okay. So this is the summarizing what I said about Webinar 1. Sorry about that. I'm looking at the wrong screen here. Webinar 2, I'd better do what I usually do and turn and face the screen. In November 2014, dealt with thermal and air quality effects on office work, that is, adults trying to work under different conditions. The work rate was 8% lower at 27 degrees when they thought it was only slightly warm when we asked them, and versus 20 degrees when they thought it was cool. If they were clothed for 25. We showed that bioeffluents and emissions reduce work rate, and that, in other words, air quality, that when the humidity is below 20%, as it often is in these latitudes in Stockholm when it's winter outside, this affects the eyes, makes them feel dry, makes you blink more often, and therefore also reduces work rate very considerably. We showed that the effects in another experiment, the effects of temperature, pollutants and noise can add up, not exactly, but they do accumulate. They're not additional in the sense that if you have the same effect of temperature and pollutants, you can add them together, but they will be greater if you add the second stressor. And we also showed that individual choice about some aspect of the environment can improve performance. Well, today, webinar 3, I'm going to tell you about 11 other experiments that I performed over the years on how other factors affect our performance. I'm very fortunate to have had the chance to study factors which you wouldn't think were part of the everyday life of an indoor climate researcher, but people saw that I could show the effects of small changes in temperature and air quality, and they asked me if I couldn't study other aspects of the daily environment. So Swegon thought it might be interesting to make you aware of those experiments too. We have recently shown for the first time that bedroom ventilation rate affects sleep quality, and that as a result of the poor sleep, it affects next day performance. That starts being interesting for our everyday habits. I showed over a course of many years, both with Swedish and Chinese children, that breakfast affects performance during the course of the morning, and in a big experiment that lunch affects afternoon performance. And then during the years I was a consultant to the Volvo Car Corporation, I got the chance to do an experiment on active safety rather than passive. Instead of protecting people from the results of a mistake, failing to see something in front of them, and improving the car's ability to protect you in those last milliseconds, I persuaded Volvo that we should actually improve the vehicle climate, the cabin climate in the vehicle, to improve driver vigilance so they wouldn't make those mistakes. And we extended that to look at airborne dust. So those are the topics that we shall be going through today in webinar 3. Starting with sleep. Bedroom ventilation is not good in most parts of the world for various reasons. Firstly, because we close the door to shut out as much noise as possible. We may also have to close the window for the same reason. Or because it's cold outside, it costs too much to heat with the window open and so on. So for various reasons, the air change rate that was measured by one of my colleagues in children's bedrooms in Denmark was poor. In fact, 57% of them were below the minimum recommended of a half air change per hour. So children in Denmark are sleeping in expensive houses, well-ventilated houses, in a very poor air quality in their bedrooms. And my colleagues in Singapore, at the National University of Singapore, they became concerned recently that more and more air conditioning is being installed in the Far East because of the heat and humidity outdoors. And where is it being run? Not, as you might think, in the kitchen or in the living room, but in fact in the bedroom, because people's main concern is to be able to sleep properly during a warm tropical night. And when they put air conditioning in the bedroom, they have to close the windows. Otherwise, they'd be trying to cool the entire Far East with their pathetic little air conditioning unit. So bedrooms are being cooled, but they're not being ventilated anymore. People used to sleep with the windows open in the tropics with a rotating fan to raise the air velocity. And that's a very comfortable way to sleep if you don't mind sweating. In really hot conditions, it's a good idea to sleep on some kind of grid so that the air can rise through what you're sleeping on. But if you sleep on a Western-style mattress, you do have a problem with sweating, because sweat can't evaporate from those parts of the body in contact with the mattress. So people are sleeping in completely closed rooms where the heat is being taken out by split cooling equipment and dissipated outside the room. And the CO2 levels are rising to 3,000, 4,000, 5,000 ppm, far more than people meet under any other aspect of their daily life. So they showed that there is a problem with air quality in bedrooms in the Far East and up here in the cool north. I think that's important because we spend more hours asleep than at work every week. So we, in fact, if you like to be pedantic, we're using more energy for providing the conditions for sleep than we are to provide the right conditions for work. And therefore, I think it's a legitimate topic for indoor climate researchers. I tried for years, at least 10 years, while I was an active member of ASHRAE, to raise some interest in research on sleep, with these arguments that I've just given you, that we have a poor climate and it is important that people sleep well for their work next day. But ASHRAE would not fund research on bedroom ventilation. The problem is that the Research Advisory Council of ASHRAE are not researchers. They think it's too complicated to do something like this. Sleep laboratories, as we all know, are often a section of a hospital. They're full of equipment. They measure EEG, ECG, and people are often hooked up to blood analysis. My point about that is that they're not measuring normal sleep. It's not normal to sleep with a needle in your arm and with 24 electrodes in your scalp, tied to the bed so that you won't rip these probes out. I think we should study real sleep in people's own beds and under normal conditions, and that's what I wanted to do. ASHRAE said it's too complicated. There are too many things that affect sleep. Well, that's true. But sleep is a behavior, just as work is a behavior, and I know how to study behavior and how the outdoor environment or the indoor environment affects behavior. And we have methods that have been developed for looking at the side effects of medication, which allow us to do this important work. In Denmark, we managed to get a modest grant for my colleague Peter Sturm-Tyson to do a postdoctoral study on sleep to show that it was possible. Unfortunately, the money wasn't sufficient to do a sufficiently large experiment, and I didn't expect it to succeed in showing actually statistically significant results. But the good news is that it did. In 2 field intervention experiments on bedroom ventilation, we studied sleep and next day performance. Sleep was recorded using actimeters that can distinguish sleep from waking. An actimeter is about this size. It's like a wristwatch. It records every movement of the body. And over a period of 3 weeks, you can then hitch it up to a computer and using validated software, find out at what point and for how long that person was asleep. In other words, not moving. And if people are even only slightly awake, they move because they're aware of discomfort here or there, or they get a bit stiff where they're lying in bed. So we can actually quite reliably distinguish between sleeping and waking state. We can't, of course, look at sleep stages, but the distinction between sleeping and waking is important for seeing what is preventing you from sleeping. And we were able to assess performance for these subjects next day using our RPM software, Remote Performance Measurement, which we developed at the International Centre for Indoor Environment and Energy, where almost all of our tests that we used to use paper and pencil for are now online. And we can measure both speed and errors on a whole range of different tasks, normal everyday tasks like typing or adding things up or multiplying them or reading or proofreading or finding errors in a text or checking columns of numbers. All that can be done automatically, and what's more important, it can be assessed automatically so that each week of experiment doesn't generate a year of analysis. The results are available instantly. So using these 2 quite recently developed methods, sleep studies using actimeters and RPM for performance, sleep experiment 1 was performed on 7 male and 7 female subjects over a period of 2 weeks in 14 identical student rooms, each of them single occupancy rooms. Each student was sleeping in an identical student room with the same furnishings and so on, and in their own bed. They were used to sleeping there. They were not in a sleep laboratory. They didn't have any electrodes in their heads, and we weren't taking blood. The intervention was to open the window on one week and close it for the other, of course in balanced order. Half of them met open window first and half of them met closed window first, in our usual way for intervention experiments. A heater thermostat kept the room temperature at the setting preferred by each subject. So we weren't asking them to put up with a very cold room just because we wanted them to open the window. They chose temperatures in the range 16 to 28. There's a surprisingly large difference in what temperature people prefer to sleep at. So I wouldn't, at this stage, claim to know what is the best sleeping temperature, but of course we could do the experiments to find out. During the 2 weeks, the average temperature in the bedroom with the window closed was 23.9 and the humidity 54%. And with the window open, you might think that that dropped the temperature because it was in a cool time of the year. But in fact, the average temperature was 24.7. So maybe they turned up the thermostat, we don't know. But anyway, there was no real difference in temperature. They were still able to choose the temperature they wanted. The only systematic difference was that the humidity was lower when we were admitting a small amount of cool air through an open window. But remember, other things come through windows. Dust, noise, any disturbance outside will disturb sleep. So opening the window is not an ideal solution. It may disturb your sleep as well as improve the air quality. Interesting small point, women selected a 3-degree higher room temperature on average. This may be to do with what they wear in bed, it may be to do with the bed clothing or how it drapes, but fact is they wanted it 3 degrees warmer. During the period with the window closed, the average CO2 level was 2,585 ppm. The range was minimum 1,700, maximum 3,900 ppm. With the open window, it never got above 800. It was from 5 to 800 with an average of 660. So you can see that the intervention was successful. Very simple intervention. No investment involved. And yet we were able to systematically drop the CO2 level by a factor of 4. And well, anyway, between 3 and 4. So it was a huge change in the air quality in the room. Well, how did that affect sleep? Sleep latency, the time it took these students to fall asleep, was reduced with the window open. Subjects fell asleep more rapidly, and this was a statistically significant effect, even on such a small, diverse group of different gender and different background, and just 7 people of each gender. So I was actually amazed that we could show this effect. Sleep efficiency tended to be increased, but we couldn't show that was statistically significant. The p-value, the probability that this observation could have occurred by chance was 0.08, and so that's not formally significant. But taken together with the second experiment, we know that it was a real effect. We asked them, of course, how they felt the next day, and with the window open, they felt less sleepy next day, p-value 0.06. They found it easier to concentrate next day, p-value 0.08. Neither of those are formally significant, but they are a strong indication that that's what was happening. We could not show an effect on next day performance in this experiment. And I think the reason is that noise and draft from the open window may have counteracted the positive effects of better air quality. And that was the reason we did experiment number 2 in a slightly different way. This first experiment was published with this reference, and I'm not going to dwell on these reference slides because you can always go back and look at them. I've given you the references of the work documenting conditions in Danish and Singaporean bedrooms as well. So you can pick these off the slide offline by returning to this presentation at the Swegon website. Sleep experiment 2, still with only an inadequate number of subjects, in this case 8 male and 8 female subjects, still for only 2 weeks, in this time 16 identical student rooms on the same corridor, and same building anyway. There was extract ventilation in the corridor and an air inlet in the wall. So the idea was that the air should be drawn into each room and then under the door out into the corridor. It's a very common, cheap solution, and it prevents cigarette smoke from the corridor getting into the rooms because the air is going the other way, for example. But as you'll see, it's not a particularly efficient way of ensuring good bedroom air quality. There can be short-circuiting. If somebody's door is open, then the resistance for airflow of all the rooms with closed doors will be too great for very much air to be pulled through it. We reduced the CO2 in the first or the second week, again in balanced order, by running a small fan installed in the air inlet. Peter chose an almost silent computer cooling fan, which only was measured at 22 decibels. That is not audible above normal background noise in bedrooms of 35. The fan came on if the CO2 rose above 900 ppm. Otherwise, it didn't. And the heater thermostat was again set by each student to the temperature they preferred. The average room temperature this time was 21.9. Operating the inlet fan did not change the room temperature. There was no difference between the two conditions of air quality. The room temperatures selected this time ranged from 14 to 28, more or less as in the first experiment. And again, women selected a 3 degrees Celsius higher room temperature than men, so that seems to be fairly common. The average humidity was again 40% with the fan operating, 52% in the week with no fan. So it's highly comparable with the first experiment. Without the fan, in other words, under the normal conditions with air being pulled through the air vent by the corridor fan, the CO2 level rose during the night to 2,395 ppm, a range of 1,600 to 3,300 ppm. So poor ventilation in this student bedroom block. And with this tiny fan operating at an absolutely negligible energy cost, the CO2 level was dropped to 835. Again, a fourfold decrease in the CO2 level. And the range was 895 to 935, so there were no peak values above 1,000 ppm, which is what is conventionally taken to be indicating poor ventilation. In other words, again, the intervention was successful. We made the change we intended to in indoor air quality in these 16 bedrooms. The results showed that the sleep efficiency was higher this time with the fan, more time in bed asleep. This time it was formally significant. The p-value was below 0.05. With the fan running, with the CO2 controlled, subjects reported feeling significantly better and feeling more rested. So these were significant changes in how they felt the next morning as a result of our change in ventilation. Now those three findings would in themselves motivate such a tiny investment in better bedroom ventilation, and I hope they will. But we went on to measure their performance too. Subjects slept objectively better and next day reported feeling more rested, as we've seen. So it's then reasonable to expect them to feel less sleepy and to perform better. So we used one-tail tests. In other words, we now had a reasonable expectation that they would feel better, feel less sleepy and work better. And with that presupposition, a one-tail test is justified and we can show that it was a statistically significant effect. The test that we used was Baddeley's test of logical thinking. So they were thinking, it's been used a lot in to show, for example, that doctors who've worked all night should not deal with patients next morning because they are not able to do as well on this test of logical thinking. So if you have a responsible job or if you really are interested in your job, you should make sure that your bedroom is properly ventilated so that you can think straight next day. You'll also feel better. Sleep experiment 2 was communicated in Brazil last October. We haven't yet published a full scientific paper on these two experiments, but we will. I'm now going to move from sleep because, unfortunately, through no fault of mine, we're only at the start of this work. As I said, I wasn't able to get the money for doing major work on bedroom ventilation. But I was invited to do a lot of experiments on breakfast and performance. Firstly by a dairy who wanted to presumably sell more milk products for people who eat at breakfast. Then by other food companies who wanted to get in on the act. And finally by the Kellogg Foundation, who funds this kind of work internationally. I'm going to tell you about a whole series of experiments where I manipulated breakfast experimentally for 81 Swedish children in 4 classes of a Gävle school while I was working at the time. Later, in 10 classes, 166 Swedish children, in 2 classes in each of 5 schools in another Swedish town called Linköping, and with my colleagues in 3 Chinese research institutes, 515 Chinese children, 12 classes, in Guangzhou, Shanghai and Beijing. And finally, back in Sweden, in an Electrolux factory, where we wanted to know whether providing a good breakfast at a factory pays. And we measured performance appropriately in each experiment. The first experiment was done as an intervention which didn't involve anything but giving instructions to 2 groups, randomly selected groups of parents. We did it in 4 classes of 10-year-old children. One of the classes, my youngest son was a student, so I was part of the home and school parent-teacher association and had good contacts with the school. I was able to persuade them to do this unusual project. Half the parents in each class, chosen at random, were persuaded to provide a poor breakfast on certain days, against their better judgment. They used our guidelines and they kept logbooks. We had pictures of a bad breakfast, which might be a piece of cake or a piece of toast and a sweet drink, and of a good breakfast, which was a whole lot more items with dairy products and grains and fruit juice and so on. They wrote down each day what their child had actually eaten. And we asked them to make excuses for presenting them with a really poor breakfast, like setting the alarm clock late, no time, sorry, you just have to take this and off you go. And the children didn't suspect that they were part of an experiment. The average nutritional values were estimated from the parents' logbooks, and as best we could, we estimated that breakfast A, the good one, provided 500 kilocalories, which is about 20% of what a child should eat in a day, and 21 grams of protein, whereas the poor one we kept down to 197, and with only 4 grams of protein. Now, that is still a breakfast. In fact, it's quite a representative breakfast for what many people eat in many parts of the world, where there's no tradition for eating a hearty breakfast. So we are not, and I want to emphasize this, in any of these experiments comparing breakfast with no breakfast. We didn't think it would be fair to subject children to being really hungry all morning. But we persuaded the parents that it was worth trying out what would happen if they didn't get up early enough to set a reasonable breakfast. On the day a test was applied, the teacher was in their normal classroom looking out over 20 children, say, and any given child could have eaten a good or a bad breakfast with 50% probability. The teachers were truly blind to conditions because the manipulation was done in the home. They had no idea, and the children didn't talk about it. We checked on that. The children did not discuss, I had a really bad breakfast today, oh, so did I. In that case, it might have got out, and we couldn't say the children were blind, but we are certain that they did not know they were in an experiment. The parents were successful in making excuses. And the teachers did not know, could not know, which child had eaten which breakfast on any given day. We compared the test results between groups, combining data from all classes. With a better breakfast, with a one-tail p-test, because we expected breakfast to improve things, arithmetic errors decreased, creative thinking improved on an open-ended test where there were an unlimited number of correct answers, and we just looked at how unique each answer was. In other words, how many of the groups gave it. Physical endurance improved. In the warm-up exercises, they were asked to run backwards and forwards until they felt like sitting down, and we just counted in which order they sat down. And logical thinking improved, not significantly, but measurably. And multiplication errors decreased. So there was an across-the-board effect of eating a good breakfast. And this was published well, presented, if you like, at the Fourth Asian Congress of Nutrition, which is how I got into contact with Chinese researchers who were also asking themselves the same questions. This conference paper is probably difficult to get hold of, but it does exist. Swedish children pilot study, we call this, because the nutritional journals would not accept this study for publication, because the nutritional intake had been subjectively reported and not measured. And nutritional experts like to know exactly what they're talking about. For me, as a behavioral researcher, the intervention was asking the parents to do one thing or the other on given days. And if there was a statistically significant difference, well, then breakfast has an effect. But they wanted to know which breakfast, how much protein, all those things that nutritional experts are paid to concern themselves with. So we had to redo the experiment. Arla, who had paid for this first experiment, is a major dairy company in Sweden and neighboring countries, and they publicized the findings anyway. They, in fact, took the unusual step of publishing my experiment with my name and everything on their milk packages. Millions and millions of milk packages. So just about every household in Sweden got to know about the results of this experiment. And as a result, Swedish parents and children started to regard breakfast as important for schoolwork. In fact, I got many messages from parents who said that this was a real nuisance, because after one parent said, I got up early, I put out everything to be a really good breakfast and expected my 14-year-old to be delighted. And when she came down, she took a look at the table and she said, where's the apple? And that was because we were showing pictures of a good breakfast, and this happened to have an apple in it. So it did lead people to be aware of the need and the benefits of eating a good breakfast. So that was the situation when we started to do the second experiment. The Swedish children were now eating a good breakfast. So in Linköping, in the Linköping experiment, we actually prepared the breakfast for them. 2 different ones, one good one, one bad one, and put them in a box, each with a date on, and on Monday we delivered these boxes to each child's home. 4 boxes for Tuesday, Wednesday, Thursday, Friday. Each breakfast box dated, and the parents served what we had provided each day, so we knew exactly what we were at least presenting the children with. And uneaten food was put back in the box and returned to us, and it was weighed so that we knew exactly how much they had consumed, provided that the parents had followed the instructions, not eaten some of it themselves. And then we were testing a method of dietary recall from a nutritional researcher. They called each child, and they were trying to estimate what they'd eaten from what the child said in the telephone interview, and we could check that against what we knew they had eaten from the analysis of what was returned in the box. So that was another aspect of the same experiment. Breakfast A provided 832 kilocalories for boys, and following nutritional researchers' guidelines, less for girls, 567 kilocalories. Each breakfast consisted of cereals, milk, bread, cheese, juice, and an apple. Breakfast B, the poor breakfast, provided boys with 197 kilocalories and girls with 147. It was just bread, jam, or cordial. And Tuesday to Friday, they either ate ABAB, good, bad, or AABA, good, bad, good, in the same class. The teacher was again blind to breakfast that each child had eaten, had no way of knowing, and the intervention was to compare more than 20% of recommended daily allowance with a breakfast providing less than 10%. Again, it wasn't absence of breakfast, rushing off to school without eating breakfast. It was a poor breakfast. With the better breakfast, again using one-tail tests, because this was our expectation, physical endurance again improved on the same test, p-value of 0.01, very highly significant effect. Creative thinking again improved, p less than 0.05. Children reported less hunger, p less than 0.001, and fewer reported feeling bad and fewer reported feeling hungry after eating the good breakfast. So that's quite a lot to get for a few pieces of breakfast cereals and milk, a few items. We as I said, we weighed the uneaten food to determine the intake. And on the day with the poor breakfast, the errors decreased the more they ate. Because even with the poor breakfast, they were all having less than 10. The more they ate, the better they did on the addition test. So there, of course, we're on a very steep curve. And so we are getting close to predicting what would happen if they hadn't eaten any. There was a correlation between how much of the bad breakfast they ate and how well they did on the addition test. So every little helps at the low end. The idea of giving children from a deprived home a sandwich when they come to school probably has an enormous effect on their ability to do school work. The work rate increased the more the boys ate. They worked faster if they had eaten more of the bad breakfast. But remember, this is only on half of the subjects, or rather only on half of the data, because here on this slide we're talking about on the days when they had had a poor breakfast. There's a lot of data in this, and I'm very pleased that these results were so significant. And this time our paper was accepted by a reputable nutritional journal, the International Journal of Food Science and Nutrition. So that is an archival journal, and this paper is readily available. After my presentation of the first experiment in Beijing, I was approached by 3 research institutions in China with the help of the Kellogg Foundation that was helping them to do this kind of research. Would I advise them on how to carry out this kind of experiment? So I made a lot of trips to China to do just that. The fact is that Chinese children apparently rarely eat any breakfast. It's just not the national habit to eat much breakfast, just as it isn't in France, or wasn't. You know, the traditional croissant and a Gauloise is a poor breakfast, and Chinese children eat apparently something like that. So we gave them breakfast A in these experiments, which was again more than 20% of recommended daily allowance, consisting of cereal, milk, bread with peanut butter, which they like, and breakfast B, less than 10%. In this case, they just got some congee, which is a rice gruel, which most of us outside of an old folks' home wouldn't like, and a steamed bun. And this provides a fair amount of calories, but still less than 10%, and almost no protein at all. In the Guangzhou experiments, Guangzhou is a city in the south of China on the Pearl River. You get there by hydrofoil from Hong Kong, in fact, is the easiest way. And it is a city that has been open to the West for a very long time. First to smugglers, of course, but later to legitimate trade. And Guangzhou is now a thriving city with multiple links to the West. They are used to having Western food in the shops and to eating it. So with the better breakfast, the Guangzhou children worked 16% faster. This was significant at the 0.01%, the 0.01 level. Their multiplication work rate was 16% faster. That's quite a big change, 0.01. And creative thinking was 18% higher on our C-score measure of originality. And they gave 17% fewer repeated answers. In other words, they thought more clearly and didn't just list the same idea in different forms. And again, as in the 2 previous experiments, their physical endurance improved with a better breakfast. In Shanghai, also a big trading city with Western food available. At that time when these experiments were done, the addition work rate was significantly faster, 12%, with the good breakfast. Multiplication, 13% faster at the 0.02 level. Logical thinking accuracy was 8% better, 0.02. Number checking, 9% faster. And physical endurance improved highly significantly. So both those experiments in Guangzhou and Shanghai succeeded in repeating the results of the Swedish experiments. And remember, we're coming from 2 different starting points. In the Swedish experiments, we were looking at what happens when children who normally eat a good breakfast don't, and for some reason. And in China, we were looking at what happens when children who normally don't eat much breakfast do. So whether you're coming at it from below or above, breakfast matters in these 2 widely different kinds of society. But in Beijing, where Western foods at that time were not available and too expensive, we could not show any effect of this intervention of offering a Western breakfast. And that's because our researchers reported that substantial amounts of breakfast day were left uneaten. The children didn't like it. They weren't used to it. It was unfamiliar with Western breakfast items, and they did not like them. So the intervention did not succeed, and there's not actually much point in measuring what the results on performance were, because they would have been dictated by chance. In fact, giving them food they don't like might have made them feel sick and had a negative effect. The summary was reported to the Kellogg Foundation by my colleagues. The lead author was Ma Guangzhou, and that report is probably available directly from him on this email address. Back in Sweden, I was asked to do an experiment on factory workers, because all this had been on children, 10-year-old children. So we found a factory where the relations between the trades unions and the management were so good that we were able to do this sort of thing. We had intended to do this experiment in the Volvo assembly line, and the relations between trades union and management were so strained at that time that it was not accepted that we should mess about with their members. So we went to a small Electrolux factory on the eastern coast of Sweden, where they were making vacuum cleaners on an assembly line, and where they kept records of how many items had passed each workstation each day and whether they were acceptable or not. In other words, mistakes and rate of working. Each worker had a buffer of items coming towards them, so the rate at which these items passed their workstation depended only on them, not on the speed of the line that was moving. So we made a bargain, or the management made a bargain with them. If they would come to work 15 minutes early for 4 weeks, the factory would serve them the free breakfast, 4 different ones. It was called as market survey, so that they could tell us what they thought they were worth. What would they be prepared to pay for these breakfasts? In weeks 1 and 4, they only got good breakfasts, but in the middle 2 weeks, they had good and bad breakfasts alternately, and that was, of course, the weeks that we were interested in. And we were able to make within subjects comparisons of their productivity in this factory by looking at how many items they had processed, whatever it was they were doing, packing them or putting in a screw or mounting the motor into the vacuum cleaner, whatever. How many items? And you're comparing each person with themselves, so it doesn't matter that they were doing slightly different work. Breakfast type A that was offered, there were 2 different versions of it, provided 590 kilocalories and 20 grams of protein. You start to recognize this now. It consisted of cereals, milk, bread, butter, cheese, juice, and fruit. Hotel-style breakfast. Breakfast type B, 350 kilocalories and 4 grams of protein, consisted either of toast or a Danish pastry with cordial. And they all thought that was rubbish and wrote down that they would pay virtually nothing for it. Some of them said outright nothing. They would never buy a breakfast like that. But they ate it and went into work. They didn't know that we had access to their productivity. But the number of units that were okay and rejected were recorded each day for each worker and work period. In the first 2-hour period after these 2 breakfast types, there was no effect of breakfast type. In other words, to begin with, even a poor breakfast is good enough in terms of doing this sort of work. But in the second 2-hour period, with the better breakfast, the work rate was 6 to 12% better, and significantly fewer units were rejected. 2 more observations. In week 1, when they were eating a good breakfast every day to get them in the mood, work rate increased from day to day, in fact, by 30%. So that might be worth thinking about for a factory. If you give them a good breakfast, if they work more than 30% better, that is going to be, shall we say, cost effective when you think how little breakfast costs and how much you're paying each worker each day. And this effect did seem to stick around, because their work rate in week 4, when the whole thing was running down, but they were again having good breakfasts, was even better than it was in week 1. So this experiment took them up to a much higher level of working, and they stayed there, at least in the 4th week. So breakfast is important for adults as well as for children, I think, is the message we have to take away from this experiment. But I'm afraid These results were never published. I wasn't paid to publish them, and I didn't have time. I was doing other things. But I was paid to look at the effects of lunch and afternoon performance. I recruited 111 students and teachers from a provincial high school, or shall we say technical school, in Sweden, to be at a particular venue between 11 and 12 o'clock. This is the only time I've done an experiment all in the same day, all in the course of 4 hours. It was bang, and it was done, and Securicor was there with the money, and we paid out huge amounts to these people for being there for those 4 hours. They were all to work in the same big hall at an individual desk as in an examination. They were used to that. They were students and teachers. And we said in the recruitment literature that lunch would be provided between 11 and 12. We randomized 50% of those turning up to eat a cafeteria lunch. And the other 50% were told that they would be receiving 2 vouchers that they could use later, all at once or on 2 different days. But today they were not to have lunch, to eat a snack, fairly substantial snack, a coffee and a Snickers bar, which is what many people think is an adequate substitute for a decent lunch. The nutritional values of the lunch we provided were 633 kilocalories, 34 grams of protein and 15 grams of fat. It was in fact spaghetti bolognese, salad, coarse bread and medium fat milk. The snack, surprisingly to me, provided 300 kilocalories, 8 grams of protein and 13 grams of fat. We should probably have provided a cheaper kind of sweet, because this almost wrecked the experiment, because it was half as much nutrition as in the good lunch. And those eating the snack were told that there was a third group eating nothing, but this wasn't true. This was to motivate them to spend 3 hours working on the basis of a snack. They thought they were lucky. Now, it was reasonable to believe that having eaten what many people consider a fairly heavy lunch, they would work worse immediately afterwards and better later on. So we expected there to be no effect or even a negative effect in the period immediately following lunch compared to people eating a snack. I think that's what many people think when they like to keep going and just eat lightly and try and force through the afternoon. The subjects were told that some people believe they work better when hungry and some don't, so that the level of motivation would not be too badly affected. The subjects were paid a generous 300 Swedish crowns plus a bonus amount for each correct answer. So they could earn up to 200 crowns more, and 500 for an tax-free for an afternoon like that is pretty good for students. And each luncheon voucher that the ones with the snack were given was worth a further 25 Swedish crowns at that time. The payment was immediate in cash, and the bonus amounts were sent to them after the data analysis had been performed. Subjects marked visual analog scales after 30, 90 and 150 minutes. In other words, half an hour afterwards, a further hour and a further hour again into the afternoon work session. And the snack, as opposed to lunch, made people feel more hungry throughout. That was a significant difference. It made them feel worse at 90 minutes, but not at 30 and not at 150 minutes. And at 90 minutes, they also said that they had more difficulty concentrating. But after 150 minutes, only the hunger was worse. It looked like this on the visual analog scales. This is a scale on the left-hand side that runs from 0 to 100. 0 corresponds to very hungry and 100 to very full. And you can see that the people who ate lunch were right up there, pretty full, 90 or something like that. And that their line trended down very slowly over the 150 minutes. And whereas those who'd eaten the snack, they started off above the halfway mark of hunger, crossed over just before the 90-minute period, and then moved down towards being very hungry during the afternoon. And how they felt was like this. The body can compensate for a omitted meal. And you can see here that there was a dip, if you like, about 90 in how they felt. In this case, the scale goes from 0 to 100, where 0 is feeling very bad and 100 is feeling very good. And they were all, and I want you to notice this, they were all in the upper half of that scale. So nobody said they felt bad. They just felt different degrees of good. And there was a statistically significant difference only at 90 minutes. So the body then mobilized reserves, and after 150 minutes, they felt just as good as if they had eaten lunch. But they still felt hungry, okay? Because on the previous scale there, they were well below the lunch group, well below down there in the hungry side. But they felt good, as you can see in the upper half of this scale. All subjects remained in the feeling good half of the scale all afternoon, though they felt worse at 90 after a snack than after lunch. And after a snack, subjects crossed into the hungry half of the scale after 1 hour and 16 minutes. So eating a snack like that will keep you from being hungry only for 1 hour and 16 minutes. After that, it's been metabolized and you start feeling hungry again. And that's why if you persist in this behavior of eating unsuitable food, you will feel hungry much more often and end up eating many more calories and putting on weight. After the cafeteria lunch, this would not have occurred until after 5 hours and 39 minutes. So a simple meal like that, single course, was sufficient to keep you from being hungry for 5 hours and 39 minutes. So you could work in the not hungry part of the scale for that length of time. And most of us, I think, can relate to these findings on the occasions when we have omitted a meal or had a good meal and gone on working in the afternoon. So remember that we thought people might work less well to begin with. It was expected that a snack would maintain performance for 30 to 60 minutes. It was also expected that a good lunch might actually decrease performance at first. But the really striking thing about this experiment, and I haven't time to show you all the detail, was that those eating a cafeteria lunch instead of a snack always worked better than those eating a snack. That is, both initially and throughout the rest of the afternoon. Even though there wasn't all that much difference in the calories, there were different sort of calories, they were quickly metabolized, and people who had eaten a simple meal ended up working better all afternoon than those who had tried to skip the meal by eating candy. This report is published with all the detail in a report to the Swedish Agricultural Research Institute. Finally, I'm going to move on to the last part of this webinar, the work I did for Volvo on active safety engineering. I've called it heat and driver vigilance. Volvo is known for its passive safety engineering. Everybody thinks of Volvo as a safe car to drive in because they were the first to introduce 3-point seatbelts. And they have put in a huge amount of really good work on crumple zones and different ways of airbags and so on, different ways of protecting you after you've made a mistake. But remember that impacts occur when drivers have made mistakes of either observation or judgment. I mean, you can always avoid an accident by not driving that day or by driving more slowly that day. So the fact that you had an accident and hit something shows that you made an error of judgment, or somebody else did, and or else you made an error of observation. Failure to observe and respond to peripheral signals is the cause of most impacts. So driver vigilance is crucial for road safety. So anything we can do with the engineering to improve driver vigilance is going to improve road safety. And just how much I am in a position to show you today. Most studies of driver vigilance are really tests of response time. They show a pedestrian jumps in front of the car, or an elk in a typical Swedish test. How quickly can you brake? These stimuli are clear and they are expected. So I don't call that a test of vigilance, I call it a test of response time. That's appropriate for a Formula One driver. It's not appropriate for a housewife going about her business in a suburb where anything can happen. There are no elks or pedestrians on a Formula One track, but there may be in the suburbs. Driver vigilance, as I define it, includes detecting signals that are initially peripheral and unclear. You have to see them, you have to interpret them, you have to think about them, you have to act according to the probability that they indicate something is going to happen. And drivers must distribute their attention optimally to detect such signals. Distribution of attention is critical to road safety. You can't concentrate on one thing just like Formula One drivers do. They concentrate on avoiding other cars and getting around the corner without spinning out. That's not driving, that's Formula One driving. Normal driving is getting from A to B without hitting anything and preferably enjoying it and doing something useful. But your distribution of attention during that activity is absolutely critical for road safety. Now, most vigilance studies are in simulators, driving simulators, where the signals are simply put in into the either on the screen or in the lights in the periphery of peripheral vision. And the thing is that subjects can redistribute their attention to where they expect signals to occur in this situation without risking their lives. They couldn't do that in my experiment. Realistic studies should be in real traffic, so drivers have to concentrate on driving. And the signals that are shown to which they must respond should be unrehearsed and undefined. They don't know what's going to happen, anything could happen, and they have to tell me what they see. Drivers should always be aware of anything that could happen inside or outside the car. So we did an experiment like that, unlike any previous experiment of this kind. Now, heat and driver vigilance has, of course, been a topic of interest for the military. High levels of heat, stress and noise, and I really mean high, where you're on the verge of collapse, and noise where you are at imminent risk of hearing damage, above 110 decibels. These two stress levels have been shown to narrow the distribution of attention. You can't think about anything else except what you're supposed to be doing. Aiming a gun or looking at a radar screen or whatever it is in these military experiments. Now, thermal discomfort in itself distracts attention, so it will distort your attentional field. If you feel you're sweating in your back, if you feel that the vents are blowing on your chest too much, you're going to get a stomach ache or a cramp. That distracts your attention from what you should be paying attention to, what's happening inside the car and outside it. And I've done a number of experiments, a lot of experiments, developing better ventilation in cars. And I know that sunshine, seat insulation and air vents in that order cause enormous thermal asymmetry in cars, greater than you'll ever meet in any other situation. And thermal asymmetry causes local cold discomfort. So drivers turn up the heat to avoid feeling too cold on some parts of the body. And warmth gives drowsiness, which leads to reduced vigilance. And these are the mechanisms that are happening in cars all the time. Distraction of attention and asymmetry, thermal asymmetry, causing people to drive around in vehicles that are slightly too warm. Thermal mannequins have allowed Volvo to optimize the thermal environments in their vehicles, trucks, buses, cars. And driver vigilance studies were then suggested to complement passive safety engineering. And the Volvo Car Corporation, to their credit, sponsored 2 field studies in a moving vehicle, which I performed for them. And they made a test car for me for these studies. Remember, this was all done before computers had been invented. So the experiment was run by a Hewlett-Packard desk calculator, a standby we had in those days, about the only kind of instrument we could program to do anything at all. In this experiment, 21 possible signals could occur at random. All of them were such that drivers should respond. For example, signal lights saying your brakes are failing, or that the engine's stopped or something. Instrument error, in other words, your instruments are showing something that's wrong, the tank's empty when it isn't, the speed is high when it's not, and so on. Motor or wheel vibration, which you should be aware of, so that you can pull over before the wheel comes off, or the engine drops out. Unintended operation of wipers, blinkers and horn, and a blue flash in one of 3 rear view mirrors. You should be aware of that, of course. So firstly, so you can pull over, but also to avoid getting fined for whatever it is you're doing. Drivers pressed a foot pedal with their left foot. It was an automatic car, so their left foot was available to me. They pressed a specially installed foot pedal to which allowed us to time their response to the signal, and then they reported verbally into a microphone what they thought they had seen. And this account was evaluated later, so that either they did see it or they saw something else and missed the signal. But in any case, we had their response time and the number of errors that they made in detection, either failing to see the signal or recognizing it correctly. Now, there were two conditions. When they got into the car, it was either at 21 degrees or at 27. We actually alternated between those two temperatures for successive subjects. And since those subjects made their appointments when they were available for the experiment, it was completely random which one they happened to meet. It would have been changed if another subject had been inserted just before them, then they would have had the other one. So there truly was a 50% chance that they would be exposed for 1 hour to 21 degrees or 27. Just a word about those temperatures. They're both in the thermal comfort range for sitting down driving. 21 is what you would probably set if you had air conditioning in the vehicle. 27 is what you would have to put up with if you didn't have air conditioning in the vehicle under the outdoor conditions where we did the experiment. Springtime sunshine, fairly cool out, but the car still gets warm because of the sun. Each subject drove for 1 hour. They made 4 circuits of a route that they were shown on a map and told about verbally. On the first time round, the experimenter in the back seat prompted them to turn at the right point, and it was both urban and rural. Into town, through town, 7 traffic lights, out of town, round on a ring road, back in on the same circuit. The observer noted route-finding errors during the second, third, and fourth circuit. The subjects were mostly professional drivers and their wives. Taxi drivers, police, emergency service drivers. We thought it would be appropriate to it would be safer to do an experiment with extremely experienced drivers, because if we had taken the subjects in a driving school, it might have been downright dangerous to distract them more by this experiment. There were 51 male subjects and 32 female, and each subject experienced only one condition. Now, over the whole 60-minute period of driving, 50% more signals were missed in the warm car at 27. This was a highly significant effect. The reaction time to the signals they did see increased by 22% in the warm car compared to the cool car. In the second 30 minutes, 92% more signals were missed at 27 degrees. And that was significant at the p.01 level. And reaction time increased by 30% in the warm car compared to the cool car. Now, those are huge changes, and they are highly significant. They cannot have occurred by chance. And this was only 1 hour. Professional drivers are expected to drive for 11 hours. And think how sensitive to temperature they are likely to be when they're tired, as well as warm. At speeds below 60, that is in town, 75% more signals were missed in the warm car than in the cool car. So it wasn't just on the long, boring motorway bypass. It's also when you're suffering from some information overload in city traffic. 7 traffic lights and lots of pedestrians crossing. Vigilance was more affected by warmth in the second half hour, as we've just seen, in city traffic than on the motorway. That was an eye-opener for us. Among younger drivers, again, an eye-opener. We had expected older drivers to be more affected. And among male drivers, again, we had expected perhaps women, who often drive less than men, or they did in those days, to be more affected. So as you're starting to get tired, you're more affected by warmth. If you're overloaded by information in city traffic, you're more affected by warmth. If you're a young driver, less experienced by definition, you are going to be more affected by warmth. And if you're male. And this is what it looks like. The percentage of signals missed for all subjects in the first half hour wasn't significant, but it was there. In the second half hour, it was highly significant, and it was even greater. You can see that the percentage of signals missed decreased slightly in the cool car. In other words, they were learning to cope. It hardly decreased at all in the warm car between the first and second hour. Their response time to the signals they did see, and that's not all of them, was much longer in the first half hour, but not significantly so. And in the second half hour, that effect became significant. At 60 kilometers per hour, a warm vehicle travels 88 meters further than one with air conditioning before a signal is detected. In other words, something's gone wrong with your car, you just go on for almost 100 meters before you even see it, before you even detect it. No, still less before you can do anything about it. And in a warm vehicle, signals are undetected at all. We cancel them after 3 minutes. They're undetected over 3 kilometers on 50% more occasions than with air conditioning. Now, these two effects have to affect road safety. You're driving down the road, you failed to cancel your indicator, it's showing that you're about to turn, so someone drives out in front of you and you think it's their fault. It's actually your fault because you failed to notice that little green arrow blinking on your dashboard. And I've seen that happen far more often on warm summer days than on cold days. This paper was published in the journal Ergonomics in 1996. That's almost 20 years ago now, and is of course available in scientific libraries. We used the same car to do a second experiment. Airborne dust, which we meet a lot of when we're driving, causes eye irritation. And eye discomfort is one more thing that distracts attention. Also, it makes you blink, and blinking slows visual data acquisition. Although you're not aware of it, when you're blinking, there is a period when you can't see anything. The world goes black. If I did it for you with a blind in front of the driving position in the car, you'd be horrified. But in fact, you're doing it yourself every time you blink. A blind comes down, you can't see anything. The brain deals with it because it's expected. So you're not even aware of it. But you have less time to see things. You're likely to miss a very rapid signal. So for these reasons, we expected that dust in a vehicle might affect driver vigilance. We used the same vehicle with the same approach, the same 4 circuits, part urban, part rural. This time we persisted and had 100 drivers, 53 male and 47 female. We used a rather unconventional method to remove the finer dust. We had a little black box underneath the glove pocket. If anybody saw it, they didn't mention it. Nobody could detect what it was. It was an ionizer. It was either on or off, just as we had either 21 or 27 degrees. When it was on, it was providing 20 to 30,000 negative ions per milliliter. And when it was off, it wasn't. Charged particles adhere to surfaces, particularly the kind of surfaces we have in cars, plastic, electrostatically charged surfaces. And you've probably noticed that happening in your car. You can write your name on the dashboard because charged particles adhere to surfaces. So the air was cleaner when it was ionized, but it's not a particularly good idea other than in experiments because particles on surfaces have to be cleaned off and filters of various kinds are to be preferred that actually permanently remove the particles that have been bothering you in the car. For males, running the ionizer reduced symptoms of headache significantly and feeling bad. It tended to reduce the number of people who said their eyes were smarting and the amount to which they felt giddy, but those were only significant at the 0.06 level. For females, for some reason, ionizer increased symptoms of headache and feeling bad. We still don't understand why that happened. But looking at both genders together, for those less than 40, the ionizer reduced symptoms of the eyes feeling dry, eyes smarting, eyes aching, and eyes feeling gritty. So the intervention to prevent airborne dust from bothering your eyes succeeded. And these figures are from men and women, even though there was some other effects of ionization. At that time, ionizing was the latest thing, and people were proposing that you should ionize instead of ventilate. That would have saved a lot of energy. But I don't personally consider it a very good idea for the reason I said. You've got to clean the surfaces, and children in daycare centers where they run ionizers go home with very black feet because the dust is adhering to the floor to a much greater extent. Overall, ionization increased vigilance for all warning lights, generator failure, parking brake left on, and the RPM being shown too high. For those under 40, where you remember there were bigger subjective effects, ionization increased their vigilance for all warning lights, 0.001, police lights behind, brake failure light, parking brake left on, engine overheating, and clock running fast. These are all signals that could occur in the car. Ionization effects were most marked in the second half hour when they were starting to feel tired, just as warmth effects were greater in the second half hour, for the younger subjects rather than for the older, and for female subjects. Ionization reduced vigilance for only one signal, when we showed speed below true speed, but as this is illegal, the possibility may have been discounted. We were indicating that they were only driving at 50 when in fact they were doing 70. We interpreted the law that since somebody in the car knew it and was able to warn the driver, the experimenter in the back had an indication of true speed, that this was perfectly acceptable. And we got away with it, and I don't mind saying that this is how we did the experiment. This kind of experiment has never been done in American universities, simply because of the risk that somebody will deliberately cause an accident and then sue the university. But the US Army contacted me after this, and they wanted to use the car to examine Gulf War syndrome, which has been said to affect people's veterans' ability to drive. But by then, the car had been scrapped. Volvo had attempted to give it to various research institutions, but they all felt it was beyond what they could maintain and would have been too expensive for them, so it was scrapped. And I think that's a great pity. Our conclusion from this experiment was that fine particles do irritate the eyes and considerably reduce driver vigilance, and that cabin air cleaners would increase road safety, just as air conditioning increases road safety. But that air ionization is not a viable solution, so I don't want anybody using this presentation to sell ionizers. This was published in the journal Indoor Air in 1995 and is readily available. That's my time. The main purpose of this lecture was to show that performance can be used as a dependent variable if experiments are properly designed, even for such odd things as breakfast, bedroom conditions, and the conditions in your car. A secondary purpose of this webinar was to demonstrate that the conditions we experience every day have quite large effects on performance. The indoor environment has a particularly large effect, and if you doubt that, review webinars 1 and 2. Thank you very much. I'm now willing to attempt to answer some questions.
Oh, thank you.
Petra says that I will answer them.
Well, I will come up. So thank you, David, for a very lovely presentation, and I'm very glad that you have been able to actually fulfill my wish, and that was to have the webinars, to have 3 webinars. The first webinar was about our children, the performance of our children, then about our performance like a normal adults and human beings at the offices. And now we fulfill the circle with what happens, what are the other factors that are influencing our performance. And I just have a question. So for all of you who wants to ask the question, just minimize the player, go and below the player you will find an image with the question mark. Click on it, and in a new window it will open a form where you can fill your email and state your question. And I will get it here on my iPad, and then I will read the question to David. And in the meanwhile, I have a question for you. One maybe, when you have done the sleep experiment, 1 or 2, did you also ask how long they slept? Like how many hours? Was it part of the experiment, or did you find out did it have an influence on the performance next day?
Well, we know how much they slept from the actimeter data, and we were only comparing the 2 conditions. Yeah. You're right that we could look at the data, combine the 2 conditions, and see how long each person slept. But we were looking at within subject changes. So it didn't occur to us to look at between subject effects of this kind. We still have the data, of course, so I will suggest to Peter that he has a look at how many hours sleep is necessary for good work. But remember, with such a small sample, we're up against inter-individual differences, which are very likely to make such an effect non-significant, even if it's there.
Thank you. And maybe one small question, because I know a bit about ppm. In the experiment 2, you choose to set the limit for when the CO2, when the fan came on at 900 ppm.
Yes.
Why did you choose 900 ppm? I would assume it would be a bit lower.
Yes, well, ideally we should all sleep in outdoor air, as they used to in the tropics, with both windows open on both sides and the breeze blowing through the bedroom. Up here in cold countries, that would be too expensive. And I know that older generation Germans like to sleep with their windows open even when it's frosty outside. And that's why they have those incredibly heavy covers on the hotel beds so that you can still keep warm. I expect they probably wear nightcaps too, as they used to in the old days up here, to stop losing too much heat from the head. Well, we did manage to keep the CO2 down to about 660, and I don't think you can do much better than that. It would be 400 if you're sleeping out under the stars, but nobody has ever suggested that there was a difference between 400 and 660. You could try setting it lower, but you would then be probably using more energy because you'd be bringing in more outdoor air. Our goal was to make sure that it never went above 1,000.
And that did not, but without the ventilation, almost 3,000, if I remember correctly. Yes. That's a lot of bad air in your bedroom. So please, if you have any questions, fill in the questionnaire and let us know. Otherwise, you can ask the questions afterwards as well, and then we will forward the questions to David and publish the answers on Swegon Academy website.
That's probably the best way to do the experiment.
That would be
I can get a better answer if I have time to think about it.
Yeah, but we have one comment. I don't think it's actually a question, and it's from Rudy Kayesi. Professor Wyon said exhaust ventilation would cost an insignificant amount of the energy only. I assume he was talking about electricity consumption of the fans only, but heating up the fresh air costs a lot more energy than moving it. This is not an argument against ventilation, of course, but for ventilation with heat recovery.
That's right. I certainly agree with that comment. Everybody thinks that ventilating is bound to cost a lot more energy. It's not true. If you open the window, then you are trying to heat the neighborhood. But if you have heat recovery from exhaust ventilation, then and a vent to let air come in, something as simple as countercurrent heat exchanger, or a more sophisticated heat recovery from exhaust air, as you have to have in Stockholm, in any building that has more than 2 apartments in it, heat must be recovered from the exhaust air, and that is equivalent to 2 major power stations or total energy stations in this city where I'm standing today. So that is a very good point, and ventilation does not mean more energy if you do it right.
Perfect. So I will check one more time if we don't have any more questions. Looks like you give an excellent presentation. So thank you all for joining the webinar, and I hope you have enjoyed it, and follow Swegon Academy for more news. Have a good day.